Today we will talk about the control of the grasp from a hand, which can be either robotic or a human hand. And we will make some simplifying assumption. Okay. We will talk about fingertip grasp in these lectures today. So we will not discuss this case, which is much more complicated in terms of control. And this makes something, this means something very important in terms of algebra, the fact that we are grasping at the fingertip. And we want to control something like the position or just balance the weight of the grasp of the object. Well, the first thing that we have to assume is something about the contact. So we assume that we have hard finger contact models, which means that at each contact point I can exchange only 3 force directions. In this case, where I have 3 contact points, I have 3 forces here, 3 forces here, and 3 forces here, okay, that I can control. So in this kind of configuration I call contact 1, contact 2, and contact 3 here, and I have 3 contact forces. Lambda 1, lambda 2, and lambda 3. All of them belonging to R3. So in this case I am showing to you today have a contact force vector which consists of 9 components, the overall contact vector. The overall contact vector is simply the vector lambda belonging to R9 and defined as lambda 1, lambda 2, lambda 3. Okay? Well, then you can imagine, of course, when you apply a force lambda onto the object, you have also a force minus lambda onto the fingers. So if you zoom one contact point, then you have the force lambda 1 inside, towards the object, okay, and the force minus lambda 1 applied to the object, to the finger, okay? Now, if you look just at the finger, okay, and you take lambda 1, look at my finger, okay? Look at the index finger. So you have lambda 1 at this index finger. Lambda 1 should be generated by 3 joint torques. And my finger, my human finger, consists of 4 joints. 1, 2, okay, here, 1 here, and 1 here, okay. But this is not independent. In some sense, this depends on this other one. There is a constraint. So we can simplify the assumption and considering just 3 independent torques for each finger. Okay? So for my index finger, for my middle finger, and for my thumb, I am assuming that I have 3 joint torques that I can independently control. So if this was a robotic hand, I have 9 motors, 3 per fingers. Okay? Well, if I want to do a force lambda 1 with my index finger, and I have my motor for finger 1, okay, which is 3-dimensional, I am almost sure that I can apply at this contact point any force I want because I have these 3 independent joint control. Assuming that there is no singularity. So what I want to say in general, if you remember the previous lecture, is that when you consider the dynamics of the hand or of the finger or of 3 fingers, Then you can summarize the dynamic of the hand in this way. So you have the inertia of the hand that depends on the joint variables times the acceleration of the joints plus a term that depends on the forces depending on velocities, okay, is equal to what? To all the forces applied onto the hand. All the forces applied onto the hand, this is the dynamics, okay? The inertial and the Coriolis forces and the other forces depending on the velocities are equal to all the external forces applied to the hand. What are the external forces? You have the independent joint control, okay, torque that you apply, and we call this tau, plus the forces that are exerted at the contact by the object as a reaction. Okay? So if you have a minus lambda force, you have plus J transpose multiplied minus lambda. So you have plus J transpose that multiplies minus lambda. So what I want to say is that you have, I'm making an example for just, I don't know, 2 finger for the sake of simplicity. And this is the object. Then at this contact you are having a reaction force that I call minus lambda 1 here, and a reaction force that I call minus lambda 2. Of course, to these two forces you have lambda 1 and lambda 2 in the other direction. And then you have the torques, tau 1, tau 2, tau 3, tau 4, tau 5, and tau 6. What I wrote here is simply the dynamic equations, okay, here, that are equilibrated or balanced by all the forces applied onto the hand. All the forces applied onto the hand are this one. Are the controlled force plus the reaction forces given to the fact that you are exerting a force onto the object. Okay? So you do a lambda 1 on the object, and the lambda 1 does a minus lambda 1 to you. And you feel it. And you have to consider in the dynamics. Okay? Okay. Now, and this is the this is exactly what I want to say here. If you focus the attention on this equation, this is the dynamic equation that holds true both when you move the object, but also when you are in an equilibrium configuration. When you are in an equilibrium configuration, all the velocities and acceleration are 0 of the joint. Okay? So at equilibrium, this dynamic equation of the hand is simply 0 is equal tau minus J transpose lambda. Because all the dynamics is 0 because you are at the equilibrium. Okay. Now, if you make some simple vectorial consideration, we said in this case, okay, you have that the lambda vector is 9 by 1. Tau is 9 by 1, you remember, because you have 3 motors per each finger. So 3, 6, 9. So this is 9 by 1, and this equation becomes tau J transpose lambda is equal tau. This is 9 by 1, this is 9 by 1, and this is 9 by 9, this matrix J transpose. What you have to assume is that J transpose is invertible. It's a 9 by 9 matrix and is invertible. So you have to assume that there exists J transpose minus 1. Okay? This is for us super simple and clarifies a lot everything. Why? Because you want to say here, look, in static equation, if you have J transpose lambda is equal tau, if someone gives you a lambda, whatever the value of lambda is, this equation is solvable, and there always exists tau that generates that lambda. Okay? So for any lambda that you want, for any lambda that belongs to R9, provided that these lambda are within the constraints and other things, but you have the power in the hand to generate that forces. You know, this is not true at all, because if I had some problem in my hand that reduced me the motion of this joint, 1, 2, and 3, like if I have only 2 motors here, 2 motors here, and 2 motors here. What happens in this case is that, I mean, consider this singular case, not this case that we just forget in a while. So you have that the lambda are still, in case of 2 motors per finger, okay, then you have that your J transpose lambda is equal tau is something like this. You have that lambda is still 9 by 1 because the physics does not change at the contact, but tau in this case is just 6 by 1. Okay, and matrix J transpose is 6 by 9. Okay, which means that for any lambda, it is not true at all that you can apply a torque to generate that lambda, because you have more equations than variables. Your variables are tau, the torques at the joint that you can apply. If someone gives you lambda that is a 9 by 1 vector, okay, gives you 9 parameter, you have only 6 parameters to satisfy those. It's not possible at all. Okay? Why it's not possible? You know, because now J transpose is 6 by 9 and that's for sure a kernel. In this case, for sure, the null space of J transpose is different from 0, and all the forces that go into the null space of J transpose are equal to 0, so you have no control on that, because even if you apply a 0 torque, lambda goes wherever in the null space of J transpose, so you cannot control it. Clear? So if you have less controllable torques than directional forces at the contacts, you cannot apply the forces that someone gives to you. Okay? And in my opinion, this is the reason why we have 3 independent joints, 3 independent motor control per finger. Because when we control an object like this in fingertip, for any lambda we want to do that our brain selects, there is enough control to do it. Clear? Okay? And this is also the reason why the first hand of Salisbury has been designed with 3 motors per finger, 3 independent motors per finger. Now, I was doing this very simply in the static and equilibrium configuration. Of course, if you take the dynamics, and you have enough control, you can always use part of this torque to do some computed control technique, computed torque technique to cancel or just change or adapt to some controlled dynamics, and you are still in the same situation. So what I said before holds true both in the starting and the equilibrium configuration and during dynamics.